Hello everyone. So in this lecture, I'm going to explain how to convert one number system into another number system. Okay. So the number system is the basic one which we are going to use in digital systems because in our day-to-day life we are using different kinds of number system. That is, four number systems are there: decimal, octal, binary, and hexadecimal. These are the four decimal number system we are using in our day-to-day life. But mostly we are using this decimal number system only in our regular working. So this octal and hexadecimal is it depends upon the applications purpose only. Okay, if it is needed, then we are going to use octal and hexadecimals. Otherwise, we cannot be used. And binary number system is a quite interesting one, which we are using inside the computer. That is in between the processor. All the communications are done by using this binary number systems only. Okay, so we'll see what do you mean the number system. So see, there are four number systems. The first one is a decimal, binary, octal, and hexadecimal. And the decimal base is 10. Why the base is 10 means because it contains only 10 numbers. See, the numbers are from 0 to 9. So 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So totally 10 numbers are there. So that's why the base is 10. And binary, only zeros and ones only used, so total two numbers, so the base is 2. And the octal is 0 to 7, totally 8 numbers are there, so the base is 8. And hexadecimal is from 0 to 9. Okay, after 9, so don't say it is a 10, 11, 12, 13, 14, 15, because in hexadecimal format it is not allowed. So after 9, we can be able to say this is alphabets A, B, C, D, E, F. So the A value is 10 and B value is 11, C value is 12, and D is 13 and E is 14 and F is 15. So totally 0 to 15, 16 numbers are there. So that's why the base is 16. Okay, and next one is which is used by humans or not. That is decimal numbers allowed alone only we are using. So remaining all other number systems are not used by the humans. Yes. And which number system is used in the computer? Only binary. Okay, that is zeros and ones only we are using inside the computers. This is what the introduction about four different types of number systems. And see how to represent the numbers in four different types of number systems. So let's take a 0 in decimal. In all the three number systems, it is represented as 0, 1. And 1 is also same. And number 2 in decimal, it is represented in binary as 1, 0, because the binary numbers are always it's having some positional weight, that is 2 power 0, 2 power 1, 2 power 2, 2 power 3, which means 2 power 3 it is 8 and 2 power 2 it is 4 and it is 2 and it is 1. So now I'm in need of number 2, right? I want to represent number 2. So where it is number 2? Number 2 is in the second position. So in this place I'm going to put 1, and this position is it is 0. And one more thing is this is LSB and this is MSB, which means LSB is least significant bit and MSB is most significant bit. That is, the positional weight of the least significant bit is very, very low, and the positional weight of the most significant bits are very, very high. So for 2, this is the representation, and for 3, 2 plus 1, 3. So these two places I'm going to put the values are 1, 1. Next, number 4, here 1, 4 is there. So in the third place, I'm going to put the value is 1. Remaining two places, the values are 0. And number 5, so 4 plus 1, 5. So these two places 1, 1, and this place is 0. Number 6, 4 plus 2 is 6. So 1, 1, 0. 7, 4 plus 2 plus 1. Number 8, 1, 0, 0, 0. Number 9, 8 plus 1 is 9. So 1, 0, 0, 1. Number 10, 8 plus 2, 1, 0, 1, 0. Number 11, 8 plus 2 plus 1, so 1, 0, 1, 1. 12, 8 plus 4. 13, 8 plus 4 plus 1. 14, 8 plus 4 plus 2. 15, 8 plus 4 plus 2 plus 1. So in this way only we are going to write all the decimal numbers in terms of a binary representation. Okay, so the important thing is the binary numbers are represented in the ascending power of 2. That is 2, 4, 0, 1, 2, 3. And these positions are having some weights. So these weights are 8, 4, 2, 1. Okay, right. So up to number 7 in octal representation, which is similar to decimal, and hexadecimal, it is similar to decimal one. Okay, next. And number 8 in octal, it is represented as 1, 0 because why it is represented as 1, 0 means in octal the numbers ranges from 0 to 7 only. When we are going to represent number 8, it will move to the second position. Yes, 8 values it is 1, 0, and number 9 values it is 1, 1, and number 10 values it is 1, 2. That is the first position value will be increases in the proper ascending order. That is, see, first it is started from 0, 1, 2, 3, 4, 5, 6, 7, and for number 8, it is represented as the next bit is having value 1, and the first bit is again started from 0. See, number 11 is represented as 1, 3, number 12 is represented as 1, 4, 13 is represented as 1, 5, and 14 is represented as 1, 6, 15 is 1, 7, and 16 is 1, 8. Sorry, 16 is it is 2, 0 because this 7 is now over in after. So the next thing is we need to increase this second bit value. So it is 2, 0. Then 17 is to 1, like that we need to increase. Okay, right. See, number 16 is 2, 0. Okay, fine. So I hope all you guys are understand how to represent a decimal number into binary or octal. Okay, right. Now we'll move to the conversion process. So there are a variety of conversion is there. That is, we are going to convert one number system into 3 other number systems. Similarly, first decimal is converted into binary, octal, hexadecimal. Then octal is converted into decimal, binary, hexadecimal. Like that, we are going to convert one number system into 3 other number systems. The first one is it's a simple example for representing decimal, binary, octal, hexadecimal. Okay, so now how these numbers are represented, we are going to discuss with some examples. So first number system is the decimal to decimal conversion. So decimal to decimal conversion, just we are going to multiply by its positional weight. So positional weight means, so the base is 10, so the 5 position is 10 to the power 1. 2 is 10 to the power 2, and 3 is 10 to the power, sorry, number 1 is 10 to the power 3. That is 1's, 10's, 100. Okay, see. So 5 into 10 to the power 0. So 10 to the power 0 value is equal to 1. So 5 into 1, it is 5. 10 power 1, which is nothing but 10. So 2 into 10, it is 20. So 10 square. So start from, sorry, 0th position, first position, and second position. Okay, 1's, 10's, 100. Fine. So 10 to the power 2, it is 100. So 1 into 100, it is 100. Now add it together, 125. See? So we have taken 125 as a decimal number. And during that conversion of decimal to decimal, we got 125, the same number. So the process is correct. So which means from decimal to one number system, if you are going to convert, so all the process are like this. That is, we are going to multiply by its positional weight. Okay, have a look at this. First one. First, I'm going to convert a binary to decimal. So this is the procedure. So multiply each bit by 2 power n. That is, the input is binary. This is the input, and this is the output. So I'm going to give the binary number first. Okay. So the question is contained binary number. See, this is the binary number, and the binary number base is 2. So I'm going to multiply the each and every digits of this binary number by its positional weight. So positional weight means it is defined by the base value. See, the first one, this number positional weight is 2 power 0, and this is 2 power 1, 2 power 2, 2 power 3, 2 power 4, and 2 power 5. So have a look at this. So 1 into 2 power 0, 1 into 2 power 1, 0 into 2 power 2. Okay, right. So 2 power 0 value is 1. So 1 into 1, it is 1. 2 power 1 is 2. So 1 into 2, it is 2. 0 into any value, it is 0 only. So 2 power 3, 8. So 1 into 8, it is 8. 0 into 2 power 4, it is 0 only. So 2 power 5, it is 32. So 1 into 32, it is 32. Now add it together, we will get number 43. So the equivalent decimal value for this 101011 is number 43. Okay. Next, octal to decimal. So octal base is 8. So here we are going to multiply by 8 power n. Okay. See, we are going to multiply by 8 power n. 724 is the example octal number. So 4 into 8 power 0, second 2 into 8 power 1, 7 into 8 power 2. So why here 8 power 0, 8 power 1, 8 power 2 is used means the given number is octal number. So the base is 8. Okay. So 8 power 0, 1. So 4 into 1, it is 4. 8 power 1 is 8. So 2 into 8, it is 16. 8 square, it is 64. So 7 into 64, it is 448. So add it together, we will get 468. And after converting the number, we need to write this suffix. That is base is very, very important, because we can say this 468 as hexadecimal also. Okay, it is possible in hexadecimal. So we need to identify the number is in the which format, whether it is in the octal, decimal, or hexadecimal. So we need to represent the base. Okay, right. Next, hexadecimal to decimal. So hexadecimal to decimal, hexadecimal base is 16. So here we are going to multiply by 16 power n. See, we have a look at the example A, B, C, and we know that A value is 10, B value is 11, and C value is 12. So 16 power 0, C into 16 power 0, B into 16 power 1, and 16 power 2. See, C value is 12, and B is 11, and A is 10. So multiply, and you will get the answer 2748 and the decimal. Okay, right. So the next conversion is, so now first we have converted binary to decimal, hexadecimal to decimal, octal to decimal. The process are just multiplications. Now we are going to convert decimal to binary, decimal to octal, and decimal to hexadecimal. So here the process is quite opposite, that is a division process. So we are going to divide the given number until the quotient is getting is equal to 0. Okay, right. Have a look at this. The given decimal number is 125. So the required number is binary. So with this binary base, we are going to divide this 125. See, first 125 divide, 62 is coming. This is quotient and this is remainder. That is 62 into 2, 124, remainder 1. Okay. Then further divide this 62 by 2. So 31 into 2, 62. So remainder is 0. 15 into 2, 30. Remainder is 1. 7 into 2, 14. Remainder is 1. 3 into 2, 6. Remainder is 1. 2, 1 into 2. Remainder is 1. Further, we cannot be able to divide this 1. So I'm going to put 0 and I'm going to write this 1 here. So while writing the answer, now the quotient value is getting 0. So now we need to write the answer. So while writing the answer, we're supposed to go from bottom to top. That is 1, 1, 1, 1, 1, 0, 1 to the base 2. This is the answer for number 125. Okay. Right. Next. Some later for this octal to binary. First, we'll move to the yes. So decimal to octal. So octal base is 8. So here we are going to divide the decimal number by 8 until the quotient is getting 0. See, the given number is 1, 2, 3, 4, and the required number is octal number. So divide by 8. So 1, 2, 3, 4 divided by 8, it is 154, and the remainder is 2. And 19, and the remainder is 2. 2 and the remainder is 3. Further, we cannot be able to divide this. So putting 0 and 2 is coming here. Then write the result from bottom to top. It is 2322, answer of this question. Okay. Next. Decimal to hexadecimal. Here the base is 16. So here we are going to divide 16 by 16 until the quotient value is getting 0. See. So 1, 2, 3, 4 is a given quotient and the required value is 16. So divide by 16 until the quotient is getting 0. So first 1, 2, 3, 4. So 77 into 16 is 1, 2, 3, 2. So remainder is 2. and 4 16s are 64, remaining 13 will come, but 10 is not allowable in hexadecimal, so we need to write the corresponding alphabets of number 13. It is D and 4. So while writing the answer from top to bottom, we need to write. So answer is 4D2. Okay, right. So decimal to binary, decimal to octal, and decimal to hexadecimal conversions are over. So the process are division process. Okay. Now we'll move to the next. Yes. Octal to binary. So octal to binary, octal range is how much? This is 0 to 7. So how to represent number 7 in binary? It is 240, 241, 242. That is see 421. Number 7, 111. So for writing number 7, we are in need of 3-bit representation. Okay. So while converting octal to binary, we are going to write all the numbers from 0 to 7 with 3-bit representation. Okay. Right. So 3-bit equivalent binary representation. So 705, what is 7? 111. What is 0? 000. What is 5? It is 101. So this is the answer for this question. So the important thing is, if octal means 3-bit representations are needed and hexadecimal means 4-bit representation. That is very, very important. Then hexadecimal to binary. See, hexadecimal, the numbers are from 0 to 9, then A to F, and the F value is 15. So for 15, how to write? It is 2 power 0, 2 power 1, 2 power 2, and 2 power 3. That is 8421. So 1111. So 4-bit representations are needed for representing this 15 in binary format. So from 0 to F, we are going to write 4 bits. See, it is a 4-bit equivalent. And 10AF, what is 1? 0001, 0, 000, and A is number 10, so 1010, and F is 4 ones. Okay, so this is the answer for this conversion. Next, decimal to octal. So, okay, this is a, we have completed. Yes. So now, binary to octal. So binary to octal, some binary numbers will be given and we are going to convert into octal. So for octal and binary representation, we are in need of a 3-bit representation. Okay. So have a look at this. So group bits in threes. So some numbers will be given. We are going to group the numbers by 3 bits from the LSB side. Okay. Have a look at this. This is the LSB side and this is the MSB side. From the LSB side, we are going to group by 3 bits. So up to here one group and here one group, here one group. Now write the equivalent octal number. This is 1 and this is 3 and this is number 2 and this is number 7. So 1327 is the answer for this question. Okay. That's it. Binary to hexadecimal. So here 4-bit representations are needed. So we are going to group all the bits by 4 bits. Okay. So see, 1011. This is one group and this is another group. So here the value is this is 2. 101, this is B and this is B. Have a look at this. So the answer is 2B. So octal to hexadecimal. So here we are going to follow 2 conversions. First, we are going to convert octal to binary. Then the binary is converted into hexadecimal. So octal to binary, we are in need of 3-bit representation. Then binary to hexadecimal, we are in need of 4-bit representation. So have a look at this. So 1076, first I'm going to write this into binary format, that is 001, 000, 7 and 6110. Now binary is over, then we are going for an hexadecimal. So hexadecimal, we are going to group by 4 bits because hexadecimal it's a 4-bit representation. So this is one group, this is another one group, this is another one. The numbers are 2, 3, 14. So 14 is represented as E. So have a look at this. The answer is 2E. Okay. Now hexadecimal to octal. Again, first hexadecimal is converted to binary. Then binary is converted into octal. Okay. See, 1 of 0C. So 4-bit representation. F is 15 and 0 and C is ABC. So 10, 11, 12. So 1100. Now group by 3 bits. So 0, 1, 7, 4, 1, 4. So 17414 is the answer. Okay, right. Some exercises are given. And this is binary addition. So we know how to add the two numbers. So 0 plus 0 it is 0, 0 plus 1 it is 1, 1 plus 0 it is 1, and 1 plus 1 which is equal to 1 0. That is, in addition, two inputs are needed. A and B are two inputs, and outputs are sum and carry. Okay, when we are adding even number of ones, the sum is 0 and carry 1 will come. When we are adding odd number of ones, the sum is 1 and carry 1 will come. Okay, so that's why while adding 1 plus 1, it is a even number, so sum is 0 is coming and carry 1 is coming. Okay, so this 1 0 value in binary representation is what? 240 241. That is, this is 1, this is 2. So 1 0 means this is 1 0 1. So 1 0 means the value is 2. So 1 plus 1, which is equal to 2. Okay, then this is one example for binary addition. See, one number is given. This is number 21 and this is number 25. Just add it together. 1 1. Let's take this first bit. 1 1. While adding, it is 0 is coming and carry 1 is here. So carry will be forward to the next position. Okay. So now 1 plus 0 plus 0 1. So 1 plus 0 1. 0 plus 1 it is 1, then 1 plus 1 0, and the carry 1 is to the next position. Now this value is there, 1 0 triple 1 0, 1 0 triple 1 0. Now what is this value? It is 2 power 0 position. So 1 2 4 8 16 32. Now at the respective places, 32 8 40 44 46. Okay, hence it is true. Okay, this is what binary addition. In binary multiplication, this is a normal multiplication, everyone knows that. And in binary, when both inputs are 1 1, output is 1. Remaining all conditions, outputs are 0, because these conditions, one of the inputs are 0. Okay, right. And first do that multiplication process, then do that addition process. And how to convert one decimal number to decimal in for fractional number. So far we have been discussed for integer number. Now this is a fractional number. Okay, so number 3, this is integer part, and this point 1 4 after a point the right hand side, it is a fractional number. Okay, right. Anyhow, we are going to multiply by its positional weight only. So number 3, we know that it is a 10 to the power 0 position, and here it is 10 to the power minus 1 position, here it is 10 to the power minus 2 position. Okay, there is no 10 to the power minus 0. It is not allowable. So that's why it starts from 10 to the power minus 1, minus 2. So number 4 portion is 10 to the power minus 2. So 4 into 10 to the power minus 2. Number 1 is 1 into 10 to the power minus 1. Okay, let's add it together. We'll get 3.14. Have a look at this. One more example, binary to decimal. So the position base is 2. So the positional weights are here minus 1, minus 2, minus 3, minus 4. This is 0 and this is 1. See, minus 4, minus 3, minus 2, minus 1. And 2 power minus 4, we can write it as a 1 by 2 power 4. It's nothing but 1 by 16. So 1 by 16 value is 0.065. And this is 1 by 8. And this is 1 by 4. And this is 1 by 2. Then adding together, we'll get the required answer, 2.685. Okay. Now this is binary to decimal. So similarly, if octal to decimal is coming means, simply here we are going to use that as a 8 power 0, 8 power 1 in the positive direction. In the fractional part, it is 8 power minus 1, 8 power minus 2. Similarly, hexadecimal to decimal, it is a 16 power 0, 16 power 1. This side 16 power minus 1, 16 power minus 2, etc. Okay. Yes. And another one conversion, decimal to binary. See, decimal number is given and binary. Yes, we know that for integer number, we are going doing that a division operation. That is for 3, I'm going to convert, that is see, 1 2s are 2 and the remainder is 1. So the answer is right like this. So 1 1 for number 3. See, But for fractional part, we are going to do that multiplication process. See, 14579 is taken, just multiply by 2. We are getting 0.29158. Now let us take this 0. This is the integer part, right? Now take this 0 as the answer. So 0 is written here. Then multiply again by 2. Now we are getting 0.58316. So again 0 is coming. So take that integer part. Then multiply by 2. 1.16632 is coming. Here integer part is 1. Let us take that integer part 1. Again multiply. 0.33264 is coming. Take this 0. Okay. So within 4 to 5 steps, we are getting here the entire term is equal to 0. Then we can stop the process. Otherwise, if the values are going means we can stop the process within 3 to 4 steps. That is enough. So in this way, we are going to convert decimal to binary. If suppose decimal to octal means here multiplications are done by number 8. Here also 8. Here also 8. Okay, suppose hexadecimal, here multiplication is by 16, 16, 16. Okay. So let me conclude. So in this session, we have been discussed the different types of number systems and how to convert one number system into another number system. Thank you.